If you want to follow along in a Jupyter notebook, you'll need to go to python.dunderdata.com and you'll make an account if you haven't made one already. Once you've made an account, you'll go to the Assignments tab. In the Assignments tab, there's a drop-down menu called Live Tutorials. You just go to that, then you'll see the Modeling COVID assignment. You'll need to fetch that assignment, and then you can open it up. So I will go back over here. So when you first log in to python.dunderdata.com, you should see a screen that looks like this, a few less files. There'll be less tabs up here, but you need to go to the Assignments tab. And by default, it's on Challenges. So you need to change this to Live Tutorials. And then you'll see there is one assignment right now called Modeling COVID. You just click the Fetch button. And when you click the Fetch button, it'll be dropped down into this Downloaded Assignments section. And then you just click on that, and that will open up the notebook. So I had some people report that they were able to successfully get the notebook. But if you have questions on getting the notebook, just drop it in the chat. And now that it's 5 after, I will go ahead and start. So again, this will last approximately an hour, with most of it being in this modeling with S-shaped curves. And the way I do these tutorials is that I have the code written out. And sometimes my tutorials, I have less code and we're going to be coding along, but this one is not going to, this is not like a coding along tutorial. This is more or less just a executing the code. So when you're following along, you'll just merely need to execute the code. In each cell, you press Shift Enter to execute the code, and that will get you through it. All right, so yes, this tutorial, I'm going to cover how I modeled COVID cases and deaths. And to see the model, go ahead and click on this link, coronavirus.dunderdata.com. So the dashboard is fairly simple and for the most part self-explanatory, but I will go ahead and cover it. So on the left side is the table and has a summary of all of the deaths and cases, deaths per million, cases per million. And you can, you can, by default, it looks at all dates. So there's 3 tabs for each of the 3 tabs above. So there's 9 total views, I guess. So you can look at the last 7 days. It will be sorted by default by total number of deaths. You can look at just the last day. You can, so yeah, at first it is just the world. So every country in the world is here. You can go to the regions tab, and let me move some of this out of the way. Like this. Each US state and some of the territories are also modeled over here. Now, you've noticed that the graph of each country or state or region is presented over here on the right-hand side. And then you can see this, the cumulative is shown. So this is a graph that will always be increasing. Right, so there's says cumulative. And then the daily number of cases and deaths. Right, and then the prediction is in orange over here. And then weekly, we have it aggregated by week. So this is the total by week. And on the bottom, you just have, a map that's color coded. And that is pinned to the the length of the, either all dates, last 7 days, or yesterday. All right, any questions before we move on from here? Oh, one thing. So you can see the model performance, how well it's done historically. So if you click on model performance, it'll go back 30 days. You can go back a little bit more. And you can see different dates. Like, as you can see here, so there was a big drop off in the second week of January in cases that was quite unexpected, and it was very fast. So the model was not able to keep up with that drop until it took a while. If you keep, for instance, moving up, right, it eventually figures out the trend and makes a better prediction. But the unexpected and very fast drop in mid-January was the model was not able to capture. So you can look at every single, some of the predictions are very bad. Some of them are a little bit better. So it just depends on the area and the time that you're looking at. It has a particularly tough time adjusting whenever there's a very sharp increase. So like whenever a model is going into exponential growth or exponential decline, those are the hardest, times to figure out where like a peak is going to be. Okay, so let's go back to the tutorial. Oh, there's a question. What are the main components used to build the system? Well, I used the Dash library from Plotly to build this, and then the data analysis is done with, like pandas in Python and SciPy, which optimizes the model, figures out the parameters. So yes, I do have a full course on how to build this. It's a very detailed course, covers everything from start to finish, and even launching it on your own server. Okay, so let's move on. So the data is from the Johns Hopkins GitHub repository, which you can click on here. I'm not actually going to talk about reading in the data and cleaning it. I want to get to the modeling part. So the data that I've given you has already been cleaned, and we're going to begin with looking at the cumulative data. So there is a single CSV file called USA cases, which actually I just ran it. I just updated it today. So it will have the most recent cases, and these are cumulative numbers for each state. And in this tutorial, I'm just going to look at a single state, Texas. We're just going to look at them, and then the same model is applied to every area. Yeah, so it has data on all the states. This is just the last 3 days. I don't know why I repeated that. Okay, so the first step that I did was smoothing the data. And here's Texas data. Now, if you look at the cumulative plot, which is what the original data has, it looks fairly smooth, right? And this is in millions. You need to take that into account if you're trying to understand this. Okay, so I noticed I just actually forgot something important. So I want to put the date in the index column. So I can actually paste that into the chat. So apologies about that. All right, so now we have the date. There we go. Okay, so this is cumulative cases. You can see there was, sort of a, I don't know, maybe not exponential, a quadratic growth, or through November, December, and January. And then things started leveling out in Texas at the end of January, early February. And now they've really leveled out recently in the last month or so. Okay, so it looks smooth. So you might think, like, why do we want to smooth this? But if you look at the daily graph, well, the daily cases are not smooth at all. And a lot of this is just due to weekend reporting. So it's a little bit of seasonality here. And some huge spikes for maybe some lag in reporting, or I'm not sure what the spikes are for. There was a recent drop for the freeze in Texas. There was a very low reporting over here. And yeah, there's just reporting oddities. There's lots of ways, holidays, of course, that the data can come back. So what you see here in the daily is not the, it's obviously not the very true number of cases that happened that day. It's just what was reported on that day. Okay, so here's some smoothing techniques. I'm just going to go through a couple of them. So the simple one is rolling average. More advanced technique is low S. So I'm going to cover both of them. So rolling average is just takes the average of the last n number of days. Here I've used 7. I've actually centered it. So what it does is it looks forward 3 days and back 3 days, and it will produce this. All right, so got the legend. All right, so here's one iteration of rolling average. You can see it's a lot smoother for the daily cases. Now, what you can do is do repeated smoothing. So that means you take the rolling average and you just do a rolling average on that. So here it's done 3 more times for a total of 4 times. And you can see it gets smoother. And if you continuously do it, it'll just end up being like a straight line essentially. So you have to be a little careful about over smoothing it with repeated average. So this isn't a terrible method. It's actually what I used in the beginning. Even just one smoothing could be good because what I'm doing is going to be modeling the cumulative. And as you saw, the cumulative is already, it's fairly smooth in itself. And actually repeated smoothing will have effects on the data, kind of moving it, because actually the end point doesn't have 3 points to the right. So you're sort of biasing it a little bit here at the very end. So this is the smoothed plot. In this one, I get the cumulative, and the way to do that, I have to add the very first value of the cumulative back to it, because I just had daily. So when you have daily, there's already some cases, right? So sorry, if I go back up here, right, we didn't start at 0. Right? I didn't begin from the very first day. There's already like 800,000 cases here. So I'm just adding that first value back here so that it aligns properly with the actual data. So you can see it follows it very well. So that looks good. So there's a question on the min periods parameter. So that just ensures that all of the, okay, by default, it will put a missing value if there's not 7, periods. So like at the very end or at the very beginning, there'll only be 4, right? Itself and the 3 before, or itself and the 3 in front. So it's not very important, actually. It just allows you to have a value at the very end and at the beginning, or also to have a missing value. Okay, so let's move down. So yes, repeated average, yeah, it's fine. Can do a little bit of bias. Low S is a little bit more robust technique, and it stands for locally weighted scatter plot smoothing. And the way it works is that at every point, it'll fit. So every single point, right? So it takes a long time. It's actually a fairly computationally intensive process, much more computationally expensive than a repeated average. So at every point, it builds a regression line from just a small segment of the data that you get to set. So it's actually better if you see the point. So let me let me plot this again. What's it called? Texas Daily. So let's just plot the scatter plot real quick. So these are daily cases. It's kind of, let me point a little smaller. Okay. So this is the same graph or same information just as a scatter plot. So low S, for instance, will say at whatever, at the November 1st, it'll pick the last however many days, like 15 days and the next 15 days, and it'll build a regression line through it. Then on November 2nd, it'll build a regression line through that one. And it uses a low degree polynomial, so 1 or 2. Doesn't try to do any fancy modeling. And then it combines all of these, it combines all of these regressions that it builds. So it builds, however many days there are. Here's 150. So it builds 150 regression models, and then it just connects them. So it's considered non-parametric since it's not parameterized by just a single set of values like a normal linear regression. As you can see, a normal linear regression would not work very well at all. And you could do like some polynomial regression to fit this, but low S is, I believe, a very good method. It'll fit, right through the pattern because it's locally weighted. So that's another thing. So what it does is it weights so at any point, it'll weight the current line more heavily than the other lines. So it's locally weighted scatter plot smoothing. So the main parameter here, and it is found, this low S is found in the stats models library. So we're going to import it and run it. And the main parameter here is this frac. So you determine the fraction of points to use for each regression line that you build. So here I just said, you can change this actually in the notebook and just experiment with how it looks. I just said 21 days, but you can change that. The smaller number is you'll have more volatility, right? So if I change this to 10, I should see a little bit more variance. If I change it to more like say 40 or something, it'll be even smoother. So you'll might miss some of the increases or decreases, but for this example, it actually looks fairly well. Now, how does this compare to the cumulative? So yeah, look, it's obviously very smooth. It's not quite right on where the actual was, and it'll turn out this doesn't necessarily matter that it's not right on if we use this data for our model, if we use the orange line, because what we're really interested in is the change in cases. So not the necessarily cumulative. So we're predicting the change, the number of new cases per day, which allows us to predict the cumulative. We can just add it onto the historical cumulative. We don't have to use whatever our actual smooth line says. So if our smooth line is off by, whatever, it doesn't matter, like 10,000, we're not going to be obviously predicting the next day we'll have like less cases than the day before. We'll just add on our predicted for our new values to the historical, the actual recorded number. Okay, so we're going to proceed with this low S smoothed curve, and we just stick with the 40. We'll see what it does. Okay, so the way I chose to model I'm modeling the cumulative historical data just with historical data. So that's key to understand how I did this. I only looked at the historical data. So just the number of previous cases is all I looked at. And obviously there's many other potential things you can add to the model. But it turns out looking at just historical data works fairly well. And we're going to be modeling the cumulative number of cases over time. And so a typical pattern that we see in pandemics is that it follows some S-shaped kind of curve where there is some period of initially starts with very low growth, and then there's a period of exponential growth, then there's a period of exponential decline, and you can see the cases in Texas sort of followed this pattern fairly close. Yeah, so it followed the pattern fairly close, at least through this time period. Of course, not all areas have followed this, natural S-shaped curve. And I'll talk about new waves at the end. So a class of functions that make this S-shaped are called sigmoid functions. And if you click on this, it's just the Wikipedia link to it. But if you look down, I believe there are more, applications, and I think it does talk about modeling pandemics somewhere. But anyways, the basic, the simplest one is just 1 plus e to the x. And here's that function. And so just to show you what this looks like, we're just going to make some points from -5 to 5 and run them through the logistic function, which is, this 1 over 1 plus e to the x. So it is, it'll have a midpoint right at 0, which will be 0.5. The high value will be 1. The low minimum will be 0. And these will be the asymptotes. So it'll just stay at 1 for all, be very close to 1 past here and very close to 0 past here. So this is the, we built, so what we're going to do is build off of this model or just change it a little slightly, but the shape is what we want. That's the important thing. So this curve gives us the right shape that will fit a typical, a pandemic for cumulative values. All right, so it is the right shape, but it needs to be transposed, right? So we're not going down to 0, we're going up. And if we just make x negative, that will transform it. So here I've just changed the function like that. So that looks good. Now, the next issue is that we want a number, the maximum, to be higher than 1. So we just multiply that by our whatever maximum we want to use. And in this case, we just, this is just going to be another parameter of the model. So we just multiply it and we call it L. And that's just the conventional letter used. So here I'm just going to use L as 10,000. So it's going to look exact same. The only thing that's changed is the y-axis labels. So yeah, this looks good, but we'll need to be able to shift it, not just have right at 0 days we have 5,000. We want to be able to shift this somewhat. And the way you do this is by so you can shift along the x-axis by subtracting from some constant, and that's what we're going to do. We're going to subtract xo, and it's known as the inflection point. So whatever you define as x naught or whatever, here I just did 50. And it looks a little different than this curve up here because I actually looked at the x goes from 40 to 60, so it covers 20 units instead of 10. So that's why it looks a little bit different here. But I've shifted it so the center, or the inflection point, is at 50. So the inflection point just means wherever the curve stops increasing. So the slope goes from, or the second derivative changes here at the inflection point. So it goes from all the points over here, it's increasing at a faster rate, and then now it's at the inflection point is increasing at a slower rate. and it is the midpoint. So this is symmetrical around here. And that's what x naught allows you to do, is allows you to just shift it. And the last thing we'll do is this curve has the same steepness no matter where it's used. So we'd like to be able to be flexible on the steepness of the curve. And sometimes it's flatter or steeper. We would like to, control that in our model. And to do that is just to multiply the x value by some constant here, which is what we call k. So this will, if it's less than 1, it flattens it out, and if it's more than 1, it'll make it steeper than it was. So here we go. We've made k a much smaller number, 0.06, but I've actually increased the x from 0 to 100. So it's covering much more distance here. And as you can see, it's much flatter. So the original was going like from 40 to 60. It would look like, I probably could have plotted it here against it, but it would be very, very steep compared to this one. All right, so any questions here on the basics of our logistic function, which is now scaled with L, shifted with x naught, and flattened with k? Okay, so I have a function here that just does the logistic, just calculates the logistic function. So it's the same that we just saw up there. So it's L over 1 plus e to the negative k times x minus x naught. And so you can play around with this if you want. If you want to take a minute here, and you can change the values of k to see what happens. So here I've done, I did 500 days, so it's actually quite a long period of time. But you can change that. You can change the maximum number, play around with that. This is the inflection point. And as you can see with this graph, the way it is, you don't actually see the end of the tail of the curve. So it's saying 120 is the midpoint right here. If you want to see the tail, you'll have to move it out a little bit to like 250, and then you can increase the k to make it steeper. And the more you increase k, the steeper it will be. So you can take a minute here and play around with these numbers to see how the curve changes. You can even change x, right? So you don't have to go from 0 to 500, but what really matters is the parameters over here, how they affect the curve. And you can make it, say, very flat by something like this, 0, 0, 1. You can see we're sort of zoomed in now right at the middle of L, which is just a million. So it's 500,000. You can see when it's very low, you barely cover any ground in 500 days. Or a little bit more. Yeah, it's just very hard. It's very faint. It still goes from 200,000, 800,000. Is k a learning rate? No, I would not call it a learning rate. It determines the steepness, or the steepness of the curve. So the higher it is, right, the less span it will take to kind of reach its minimum or maximum, although it never, it's an asymptote, so it never actually reaches that. But practically speaking, it does. So here I'm just shortening the time it takes to go from a maximum, or from minimum to a maximum. Right? So originally I had it at 1, but this will be extremely steep because I'm just looking at so much. I've expanded the x so much. it's 500, whereas above I was just zoomed in. If you look up here, we were just looking at a span of 10 across the X. So that's why it looks so steep right here, because we're looking at 500. So let's go back to something a little bit more, even something at like 0.2. And this, it's the reason these K has to be so low here is because I've used 500 points. All right. So maybe you can use this to manually fit the logistic function. So we'll take a little break here to see how you can manually fit. So what I've done here, we're just going to assign this to a shorter name. It's called Y Texas. So this is just the cumulative values. All right, so manual fit, all it does is you give it the actual data. So this is going to be Y Texas. And what it'll do is the model will just be the parameters that you give it. So for L, X naught, and K, you have to give it in that order. Right? It's the same order that was defined over here in logistic func or logistic. And then it'll just plot them. So let's so you can play around with this and see if you can model it. So here's Y Texas, and you might want to look at. I guess we'll see it when we model it. So and so the number of cases was right around 3 million at the very end. So it needs to be at least whatever the maximum value is. This is going to be L, right? So this is parameter L. Oh, sorry, I have func here. So sorry, I need to put in the function. So put in logistic here, and then we're going to pass in the parameters. And I take that back. So what you need to do is, let's make the parameters here. You have to put it in a, a list or a tuple. So sorry about that. So you do this 3 million for L. Let's say X naught will be 50 days, and K will be 0.1. Okay, so now we can put here in params, and you can get the fit. So what I want you to do here is play around with these numbers until you get a decent fit here. So one of the issues is that it would be a lot easier actually if I made this 0. And we'll take care of that. And that's because there were further waves in Texas, or earlier waves, in the summer. So there was like another S curve in the middle of 2020. So this is a little bit unfair to this to the logistic function the way it is right now, because it's not starting at 0. But anyway, regardless, you can still get sort of a decent fit if you play around with these numbers enough. And you can see right now it's way too steep. So I know that I need to decrease K to make it smaller, because it's going way too steep. So maybe I go to 0.05, and it's looking a little bit better. And it looks like 3 million is probably maybe too much. So maybe go down to 2.9 million, or even, a little bit less. But it still looks a little too steep. Let's maybe go down here. So, it's not the best model, but you can get something that sort of, looks like it. So take a minute here. We'll just break for, say, a minute. You can drop some questions in the chat if you have them. And see if you can find a good fit here. Okay, if the kernel has died, there might be a lot of people on the server right now. Maybe you can restart, and if you go to kernel, restart, and clear output, and then run all the cells. Maybe that'll work. Yeah, so the notebook will be available, forever. Yeah, you can download the files, right? So you can just go over here and you should be able to just click them and download them to your local machine. So you can do that. There should be a button that says to download. Like if I'm over, yeah, I'll just leave it to you. You should be able to download it. So apologies about that. It's probably the most people I've had using it at one time. All right, so let's, instead of manually figuring this out, right? That's going to be a very difficult task. We can let some optimization routine figure it out for us. And SciPy, which is a module or package in Python, has many optimization routines. And it has a whole module called optimize. So there's a least squares function in the optimize module, and that will find the parameters of a function that you give it, and it will do so by minimizing the squared residuals. So it'll find the model that, it'll subtract the model from the actual, it'll take the squared value and sum up all of those squared values and try to find the parameters that minimize it. Now, it doesn't always succeed in finding the minimum. It's not a guaranteed, it depends on the function you use, actually, to figure out whether or not you can get more of a guarantee of finding the minimum. But regardless, it should, in most cases, find a good model if the function is, simple enough. So in order to use it, you have to make an optimization function. And the optimization function returns the error. So what this optimization function takes in, the first value is the parameters, and these will be a tuple, or just, some sequence of parameters. In this case, we have 3 parameters, so it'll be a sequence of 3 values. Now, this is, these will be more or less static, x, y in the model. Right? These will be constants, actually. X will just be the x values, y will be the y values, and model will be the actual function. So I'll show you how these get passed in. But regardless, what happens is the model, or we're going to get the prediction by, passing in the parameters to the model, and then we'll just subtract that to get the error, and we will return the error. So that's what this function does. Now, the way to use least squares, so I imported up here. What you have to do is you have to have bounds for your parameters. It does not, I think some functions might not need bounds, but the least squares does. So here I've come up with bounds for the parameters. So these are bounds for L, XO, and K. So and what you have to do is you have to pass it, you have to store it as a list or a tuple of tuples, right? Like a tuple of 3 item sequences, right? So you have the lower bounds and the upper bounds. So here the lower bounds, this will be for L, this will be for X naught, and this will be for K. So the lower bound for X, or for L, should at least be the maximum value now, right? So you can't have an L that is less than the maximum now, and that's what this is doing. So right now it's about 2.8 million, and that's what will be the lower bound. Now the upper bound, for pandemic, it's very hard to know what the upper bound is going to be, but I just put the number 4 million. I'm not going to discuss, ways to guess at upper bounds, but that's a whole nother topic. For X naught, I put between 20 and 150 days for it to reach the inflection point. And then K, I have, this is the steepness from 0.01 to 0.5. So some of these, these were sort of come up with after doing some experimentation. Now you also need an initial guess. So I'm going to say my initial guess for the L, the maximum value, will be 3 million. My initial guess for X naught will be 50. And my initial guess for K will be 0.1. Okay, so I get X and Y as NumPy arrays. And the way least squared works is that you pass in the optimized function that has to return the error. You then pass in the initial guess. That's your guess. These are extra arguments passed to the function. So what I've done here is I'm passing X, Y, and logistic. So these will get passed in right here. So X is just the X values, which are just the integers from 0 to n minus 1. Y are the actual number of cases, the cumulative number. And then the function that I'm optimizing is logistic. So that'll be called model over here. So it gets passed in over here. Then I give it the bounds. And this verbose is just to see the output. You don't need this. This is just for us to see it in the notebook. And if we run this, you'll see each iteration and then the cost function. And then how much this is like the, I'm not sure if this is the squared error. It might just be the sum of the squared errors. And then how much that cost function is reduced. And then there's some stopping criteria for least squares. So you have to read about them. There's actually many different, there's multiple stopping criteria that it uses. So you have to, there's a, the documentation is very thorough. So you have to read about when does it say to stop, and you can change those criteria. Okay, so it successfully, stopped. It didn't go past like it also stops if there's too many iterations, and it'll tell you like it failed. And so this one did not stop it. See, it said this termination condition was satisfied. So whatever this F tolerance termination is, it was satisfied. All right, so now we can see the parameters that it found. So it returns this object, this, it's like essentially like a tuple. But if you do dot, you can see all of the attributes here, and you can see, you can kind of go into the optimization. But what's important for us are the parameters, and those are in X. So it came up with 3.7 million, a X naught of 85 days, and then a K of 0.016. So what we can do is, why don't we just see what this looks like? And so it found this, and this would have taken us a very long time, obviously, to do it manually. And it looks, fairly good. It's probably gonna way over predict in the future, but it's trying to match the current curve as it sees it. And this is not the right model right now, and we'll see a better model in just a little bit. All right, I'll answer some questions of those later, maybe after. If you have, yeah. It's probably better to ask the questions on the, the model itself. I can ask the pure Python questions at the end. Okay, so we can actually build a better model. And so one issue with the logistic function, the way it is that it is symmetric. So it doesn't allow for asymmetry. So if you have a long tail, say it takes a longer, say it takes only 50 days to get to the midpoint, but 100 days to reach its end, you cannot use a, just a regular logistic function. So the generalized logistic function, it's called generalized because this is like the most parameters that it has, gives you a way to have an asymmetric S-curve. And this will prove to be a much better model than the normal logistic function. So its form is like this. There is no X naught, but this V controls the horizontal shift. I've also added a vertical shift up here. So this minus S and then plus S will account for the vertical shift. All right, so here's the function in Python. And here's our new, so here's our new model. And the way now it's written is that we can pretty quickly see how this model works. The only thing we need to do is change the bounds, change our initial guess, and then the least squares call is just about the same. We just change the function over here. So I have L, K, V, and S. So the shift, that's quite important here because it didn't start at 0 cases. If I started in February, I could have used it. I actually would have gotten decent results with Logistic, with just the plain Logistic, if I used from the very beginning and stopped at like some point where sort of the end of the first wave. But I've started in the middle where many hundreds of thousands of cases have already occurred. So this function is actually going to go to 0, and that's sort of unfair to it. So I probably could have done one more step with the normal logistic and did this vertical shift with S. Okay, so let's see how this one works. So it's just about the same code. V, just some experimentation. You can change these numbers. I just put between 0.01 and 1. Okay, so we run this again, and it actually terminates almost at the same time, but it has, a different function. You can actually see the cost is less. So remember, it was something to the 11th power, and this one is to the 10th power. So however this cost is measured, it is less than it was with the first one. So we can look at the values here, and we notice that the L is a lot less. So the maximum value here is way less, which to the eye seems much more reasonable. It has a smaller K, so it allows for a little bit of a more flat. And then here's the vertical shift. So it's allowing it to shift almost exactly what it was at the beginning. So this is about 800,000. And this is a key to making the model work out better, is this vertical shift. All right, so now we can plot it with this manual fit, and you can see we get a much better curve. Now, this is modeling on data that we've already seen. So this is not indicative of how it'll perform. And in fact, it already looks like it's going to be off in the future, as it's probably predicting it looks like it is steep or it's flattened out the curve, and our model is going to be predicting a little bit higher growth rate. But anyways, regardless, you can see that it does generate a fairly good fit. And so this is sort of the basis of the model that I use, was this generalized logistic function. Okay, so modeling deaths. So that's cases. So deaths also follow a S-shaped curve, and you could use the same procedure. Now, the only issue is that if you model them independently, it's possible that you get, pretty different results for deaths and cases. Maybe in sometimes, results that don't make sense. Maybe you have more deaths than cases or something like that. So a different way, and this is what I actually used, was to use the historical case fatality rate. So the case fatality rate is just the number of cases that lead to a death. And there's usually some lag, right? Because people don't die immediately when they contract COVID usually. There's some period of time where it takes before the person dies. So, and I'm not going to programmatically do this, I'm just going to talk about it, but what you can do is, so this is very simple, is that you just find the most recent case fatality rate. So you can just take the number of cases that say happened between say 20 and 40 days ago, and measure the number of deaths that happened between say 0 and 20 days ago, and use that as the case, and just multiply that case fatality rate by the number of cases to get a model, or yeah, to get a prediction. So even something like that can work out fairly well. And that's actually what I did. So I did this simple model for deaths. I didn't actually use a logistic curve. All right, so we're coming towards the end, a note on ensembling and modeling new waves. So, right, so if we look at all of the Texas data, and maybe I should do that real quick, so apologies for scrolling up, but let me get these, and instead of doing just the last 150, I will just get all of the data. And if we plot all of it, you can see there are, about two waves. You could say one in the summer of 2020, and then another in, starting in the fall. So using a single generalized logistic function will not work very well at all with this. It's only meant for a single wave. Now, so there's a couple of ways to do this. And so you could try to model from the beginning, like a single curve. And I think that's a very difficult proposition because many things change, like just the number of ways, the data is being tracked or whatever. But there is a way you can actually model L, which is the upper bound, right? It's that upper asymptote as a logistic function itself. So L can change over time. So it could start out at like 1 million or whatever, but then as we get over here, it can end up as 3 million. So it allows for, multiple waves. Now, a big issue with that is that it increases the parameterization of the model significantly. So it makes it now SciPy, or the optimized routine, is instead of optimizing like 4 parameters, it might be optimizing like 7 or 8 parameters. So it makes it much more computationally expensive. It makes it much harder for it to find that, local, minimum, and it might get caught in different local minima that are not, um, that might not provide a good solution. So while that can work, you can write a much more complex function. And I did that, and the results were okay, but it turned out that I got better results if all I did was if I just modeled, like, say, the last n number of days. So what I ended up doing was, I just looked at the last 100 days or 50 days or 70 days, and I built models based on that. So it would essentially forget about the past. So whenever it was entering a new wave over here, it would have only known, say I'm in November, it would only look at maybe data from, like September. It wouldn't go all the way back to May to look at that data. And it's sort of irrelevant to the current wave. And the way I ensembled, which just means using multiple models, that's what ensembling means, is that I would choose many different days to look back. So I'd say, all right, I only look back 30 days, then 50 days, 70 days, 100 days. And I would do all of those combinations and bring in all of those estimates together for a final prediction. Now, there's certainly different ways you could go about doing this, but I found that to be pretty simple, and it worked decently well. Okay, so that essentially wraps up the presentation on how I modeled COVID cases and deaths using S-shaped curves. So hopefully that was of interest. I see a lot of questions, so I will get to them, or at least a few questions.